Okay, define Bernoulli trials and binomial distributions. This is 14a. So, Bernoulli trials are situations where you'll have only two possible outcomes. Typically, you describe them as a success and a failure, but it can be A and not A, whatever wording you want to use, where your probabilities remain constant between multiple trials, and each trial is independent. So that's a lot of words. Best to give an example. So if I'm rolling 1d6, so a single six-sided die, and I'm rolling it, I'm going to define success as rolling a 5 for whatever reason. Well, okay, what's the other side of that outcome? Well, not a 5. So 1, 2, 3, 4, or 6. All of those are failure. So success is a 5, failure is anything else. Okay, fine, so that satisfies my two outcome thing. So even though the dice can have 6 possible outcomes, I'm going to restrict that down to 5 and not 5. So that satisfies that condition. Probability is constant. If I roll the die, every time I roll it, it's always 1 in 6 chance that I'll get a 5 and always a 5 in 6 chance that I won't. It doesn't change over time for any reason. And kind of inferred from that is that each trial is independent, so each roll of the die, the first one doesn't affect the second one, doesn't affect the third, doesn't affect the fourth, the first doesn't affect the fifth. There's no interplay between them. Each roll is totally independent of all others. Cool. So each roll would be a trial, and then you can have what's called a Bernoulli sequence, which is a repeating of the trial. So trial 1, 2, 3, 4. Binomial distributions basically take care of that. It's when you have a Bernoulli sequence. It's when you've got multiple trials in a row. Beautiful. Okay. So how do we calculate the probability of certain things happening? So ultimately what we want to get to is these sorts of scenarios. What's the probability of exactly 3 5s coming up if I roll 4 dice? Now, to be clear, I could roll all 4 at once, or I could roll 1, 2, 3, 4 and go and look at them as they come. It doesn't actually matter since they're all independent. Doesn't matter if I do them all at once or one after the other. Beautiful. So how do we figure this stuff out? Well, if we think about it, one die at a time. Okay, I've got a 1 in 6 chance of it coming up there. Okay, fine. I've got a 1 in 6 for each of them, so that's all great. I need 3 out of the 4. Okay, so I could have either 5, 5, 5 and not 5, or 5, 5, not 5, 5, or 5, not 5, 5, 5, or not 5, 5, 5, 5. So there's 4 possible arrangements that would give me that scenario. Well, that's okay if I want to count on my fingers all the time, but if these numbers were bigger or a bit more fiddly, that might get a bit troublesome. So we should think, oh hang on, we're back in combinatorics land because I'm asking how many ways can I get 3 out of 4 sections. So we're dealing with combinatorics again. Alright, so that's where this guy's come in. So n is going to be my number of trials or attempts, and x is the number of successes I require. Great, okay, so that's how many ways it can happen. What do I want to happen? I want to roll a 5. What's the probability of that? Well, it's 1 in 6. So I'm going to have that, but I need it to happen however many times, 3 in this case, so probability of success multiplied by itself however many times. But I also need the remainder to fail, therefore probability of failure, which is 1 minus the probability of success by default. All that gets raised to the power of however many other trials there are. Well, there are n trials, x of them were successes, so n minus x must be the number of failures. So overall, we've got this thing. So this is just saying the probability that my random variable gives me exactly this many results is equal to the number of trials, combinatorics with the number of successes, multiplied by the probability of that many successes, multiplied by the probability of that many failures, where all of these are, where n and x are both positive integers, and x is somewhere between 0 and n. So you could have 0 successes, you could have n successes, or anywhere in between. Oops. Beautiful. So I've got n, x, and p are our only variables in there. Okay, fine. Well, let's go back to our scenario. Probability of exactly 3 5s on 4d6. Okay, so what do I want to have happen? I want exactly 3. So I want 3 successes. Okay, great. How many trials do I have? I have 4 trials, so I've got 4, and I need 3 successes. Okay. My probability of success, it's on a 6-sided die, so that's 1 in 6. Did I leave space for that? Yeah. 1 in 6 here. Make sure I put brackets around, just so it's clear. Cool, I need that to happen 3 times. Okay. I need it to not happen 1 minus 1 on 6 times. So I need it not to happen, so that's the probability that it won't happen. And I need that to happen however many remaining times I've got. So I had 4 in total, minus the 3 successes, gives me 1 time that it has to fail. Okay, great. Well, 4C3, we can go through a calculator and do it that way. You can go through other tables and everything as well. But we end up with, do I want to do it in, yeah, I'll do it in that color, it's fine. 4C3 is going to be 4. This to this is over 216 is 5 on 6. 4 minus 3 gives me a 1, so it gives me that. Gives me what? 20 over, here we go, 6, 3, gives me 9, gives me 12, I think that's right. Which equals what? Divide by just 2 is going to divide by 4, yeah, I can divide by 4. Gives me 324, done. Which, if we change out to a decimal, divided by 324 is, yep, roughly 0.0154, something, something, something. Beautiful. Now, if we've got numbers like this, it's not the hardest thing in the world. There's a bit of fractions and stuff in there, but it's just a little bit of fiddling around. All right, well, if these numbers get too big, that's going to get really fiddly, particularly for the combinatorics part. And if the powers start going off into like 7s and higher, it'll just be rather tedious. So instead, we can use the CAS for this. So if you go into the CAS menu, 6th option is stats, 5th option in there is distributions. Then there's a huge list, and it's actually easier if you hit up to go to the bottom of the list so that you can get to the letters at the bottom. Binomial PDF, there's also CDF, you want PDF for this. It'll open up a table where it will ask you for, it'll ask you for number of trials, probability of success, and how many successes you want. And so you fill that in, unsurprisingly. When you fill that in for this particular one, you're going to want 4, 1/6, and 3. It'll spit out this in your actual output, which will be roughly whatever number that is. So that's all well and good. So PDF is short for probability distribution function, which means that you're looking for one specific set of outcomes. So in our case, we're looking for 3 successes. So that's what the PDF means. We could take this a step further and go, well, hang on, what if I want at least some number? So at least 2 5s on 4d6. So I might be able to, I might get 2 5s, I might get 3 5s, I might get 4 5s. Okay, great. Well, probability that my thing is, that my variable is greater or equal to 2 of these. Well, one way of thinking of it was what we just said, getting 2, or getting 3, or getting 4. But we could rethink that and go, well, hang on, that's the same as everything minus the probability of getting none minus the probability of getting 1. Now, if you take a look at those two, this one is definitely going to be easier to calculate, because minus the probability of getting none, well, that's easy, that's just all of them fail. So we can go, alright, that's 5 on 6 to the power of 4, minus probability of getting 1, well, how many combinations are there? There's going to be 4. Multiplied by probability of success, 1 on 6, once, multiplied by probability of failure, the other times, which would be 3. So that's actually a reasonably short way of doing it. You could do it this way, but each of those expressions is going to be as long as that. The last one, not necessarily. But the first one's going to be longer. So you should always think, hang on, am I doing this the most efficient way possible? And we get whatever we get for that. Actually, no, let's do it exact still. So I've got well, 1 minus whatever this is. Let's go. I'm going to keep this as 6 to the 4 on the bottom. 5 to the 4, so what do we get? 625 minus 5, no, yeah, put it that way. 5 to 3, 125 over 6 to the 4. Now hopefully we notice we've got all 6 to the 4s on the bottom. So we can say, okay, this is 6 to the 4 minus 625 minus whatever this is, 500. Cool. So we could simplify that even further and say whatever 6 to the 4 is minus 1125 over 6 to the 4, which roughly equals some terrible number, I'm sure. 6 to the 4 is what? 1296. Oh, actually, let's replace that because that's way more reasonable. 1296. Nice and squeaky today. 100 and what's this? 171. Yep. 171 on 1296. Hopefully I've done that right. Yep. 0.1319, and then there's a bunch of 4s after that. Beautiful. Now, that was a fair bit of work, particularly if these numbers get bigger or if we've got more trials, that could very quickly become cumbersome. So we've got the CAS again. So you go through the exact same starting menu, stats, distribution. This time instead of binomial PDF, we're going to pick binomial CDF, cumulative probability density function, or cumulative density function. This time you'll get an extra input to put in, which is, so you've got your number of trials, probability of each individual success, then minimum number required, maximum number required. So for us, the minimum was at least, so 2, and the maximum is however many trials we got, which would be 4. Bang, that's the output you'll get. Essentially what that's doing is counting up everywhere in between. It's actually doing it in a smarter way than that, but that's the basic way to think of it. So just for your notes, PDF is when you want a specific number of outcomes. CDF is when you want a range of outcomes. And that's that. That's 14A. Cool. Any troubles, email me. Otherwise, best of luck.